This is chapter 12, and we're going to study exponential functions. And to do so, to see what they look like, why don't we let x represent a variable, and we'll let b represent a constant, like 3 or 4 or 5. Now, the functions that we've been looking at so far have been algebraic. So algebraic functions, how about Fn for functions? Algebraic functions look like this. Maybe like y equals x to the b, where we have, well, here's an example. Say we have y equals x to the third, and the form that we have is this. We have a variable, so y is equal to a variable raised to a constant. Now that's algebraic. Now, exponential functions, on the other hand, here's what we're going to do. We're going to take this algebraic function and just switch the order of these. So instead of x to the b, what we're going to have is b to the x. So in this case now, the variable appears in the exponent. So we're going to have, here's an example, something that looks like this. Instead of x to the 3, we will have 3 to the x. So we have this form here, y equals a constant raised to a variable. Now let's look at some problems. So here's a problem here. What do you think about this function here? Is this an exponential function or algebraic? So what we have here is that we have the variable in the exponent, the base is a constant, the variable is in the exponent, and because the variable is in the exponent, this function is exponential. Now, if we had this one, y equals x to the 8th, that's algebraic. So what do you think about this function right here, y equals x to the 4th? Well, the way I look at it is the variable is in the base and the constant is the exponent. So I think we've got something like this. The variable is in the base. The exponent is a constant. So this function is algebraic. And the question is it exponential? Is this exponential? The answer is no, it's algebraic. Problem number 3, they're asking us in this exponential function to identify the base. Now it is exponential, right? Because the exponent here is a variable. The variable's in the exponent, and it applies to what's directly below it, which is pi. Now pi is a constant, right? 3.14 ... So the base here is pi. Don't think that 0.9 is included because the x applies only to the pi, not the 0.9. Otherwise, it would be written like this. We'd have like 0.9 pi, all of that to the x. But that's not what we have, just the pi. Now, exponential functions can look like this. When we graph them, there's going to be one of these two types. So this is x, here's f, x, and f. Now, an increasing function is going to look like this one here. And in this case, what we're going to have is, now, the general form of an exponential function is going to be this. It's going to be y equals b to the x, where b, now that's the base here, the base has to be greater than 0. So, looking at our number line out here, the bases are here. No negative bases, right? The base is greater than 0, so it's off to the right. It's not 0. It's off to the right. And not only that, but it cannot equal 1. So a legitimate exponential function is going to be b to the x, where the base is somewhere in here between 0 and 1 or greater than 1. We do not allow 0 or 1 or any negative numbers. Now, if we choose a base in here, like, 1/2, 1/3, some number between, strictly between 0 and 1, we're going to get a graph that looks like this. It is a decreasing function that continuously decreases like this. It starts up high and then decreases toward the x-axis, toward y equals 0. So this is the graph of the function y equals b to the x, where b, the base, is some number between 0 and 1. Here's an example. Here's an example. Y equals 1/3 to the x. So this is a decreasing function, and it's always decreasing. This function always decreases. Now, if we pick a base that's bigger than 1, like some number bigger than 1, like instead of 1/3, suppose we pick 3, we'll get a graph that looks like this. This is an increasing function. Looks like this. So this would be the graph of y equals b to the x. An example might be y to the, now base is bigger than 1, so it's going to be 3 to the x. This is an increasing function. Now notice here, in both these graphs, I'll do it right up here. If x is equal to 0, then you get y equals b to the 0, but b to the 0, that's a 1, because remember now, the base cannot equal 0, so we don't get 0 to the 0. So we have a non-zero number to the 0 power, which is 1. So if x is 0, now follow this back down to the graph, like over here. If x is 0 right here, then y is 1. So this curve goes through 1 on the y-axis. And it also goes through, if x is 0, y is 1. On this graph here, if x is 0, we're right here. It also goes through 1 on the y-axis. Now, I'm going to go back down to these functions down here at the bottom left here. If it's a decreasing function, we have a name for that. That is called exponential, I'll abbreviate, exponential decay. Decreasing functions are called exponential decay functions, and increasing functions, like this one here, these are called exponential growth. Exponential growth functions. So if it's decreasing, it's called decay. If it's increasing, it's called growth. So this function up here in number 4, it's increasing. It's going to have a graph that looks like this, and it's going to be called a growth function. So this is increasing, let's call it a growth function, and the graph would look like this. Now, in number 5, we actually want to compute f of negative 3 for this function, right? Now, what kind of function is it? 4 to the x. The base is bigger than 1, so this is going to be a growth function. What is 4 to the negative 3? So we're going to evaluate this function, and we'll do it as we normally do. Everywhere we see an x, okay, here's an x and an x. I'm going to write an open parentheses there. So this is going to be x open parentheses equals 4 to the open parentheses. Now what we're going to put in here is the negative 3. I'll put a negative 3 here and a negative 3 here. So we will get f to the negative 3 equals 4 to the negative 3. But now let's eliminate that negative exponent. This is 1 over 4 to the positive 3, which is 1 over 64. Now, number 6, let's just identify this type of function. First of all, the base is a constant. The variable is in the exponent, so we know it's exponential. And more than that, because the base is positive, we know that this represents an exponential growth function. And growth functions look like this. Now, in this particular problem, we're given parts A, B, C, and D, and asked which one is it? Is it A, B, C, or D? Well, A, here's what A looks like. A looks like this. It's a straight line. Okay, no, this is not a straight line. It looks like this, right? It's an exponential growth. So it's not a straight line. And then B, okay, B looks like this. Okay, well, our growth function doesn't look like that, so that's not it. Here's C. C looks like this. I think that's it. Let's just check D. D, the picture I'm given here in D, looks like this. So the only one of these functions, 1, A, B, C, or D, that looks like this one is C. So we'll conclude that our answer here is C. Now we want to graph this function, so it's exponential, right? The variable is in the exponent, so it's exponential. Let's make up a table. Let's get some values from our table, so we'll get maybe x and y in our table. And how about this? When x is 0, what we're going to get here is 0.2 times 5 to the negative 0. That's 0.2 times, now to the 0 power, right? So we're going to get a 1, so this just is 0.2. How about when x is equal to 1? So we'll get 0.2, 5 to the negative 1, that's 0.2. 5 to the negative 1 is 1 over 5 to the positive 1. So we get 0.2 times 1/5. Now 1/5 turns out to be another 0.2, so we end up with 0.04. So when you can do this on a calculator too. So when x is 1, we're way down here at 0.04. So now look at the graphs they give us. They give us graphs for A, B, C, and D. We can rule out a couple already. First of all, A, no, it's not exponential. Exponential, you know, goes either increasing or decreasing. What about B or C or D? Those are possible. But now as I look at this, I can rule out C. C is not going to work. Can't be C, because what's happening is as we go out to 1, right, we start here at 0. We're up at 0.2. Then we go to 1 and it's decreased. It's decreased. So C, this graph is actually increasing, so it's not that one. So if we put in negative 1, we'll get 0.2 times 5 to the negative x, negative 1. This is 0.2 times 5 to the 1. That's 0.2 times 5, which turns out to be 1. So here when x is negative 1, we're going to get y equal to 1. Now look at these graphs. Could it be B or D? Well, I'm thinking this is going to be the graph in D, because as I look at D, if I go to the left one, right, at negative 1, we're supposed to go up 1. So I see if I go to the left one, it looks like we're up here at 1. That doesn't look like it happens in B. Now we've got a word problem here in number 8, and what this all is M is the number of small mammals and on some property, and T, now look, our variable's in the exponent, so we know we have an exponential function. So T is in years. In fact, it's in T is in years. It's the number of years after the birds decline. Now, look what we have here. This base is bigger than 1. The exponent's a variable. So what we have here is we have an exponential growth function. And growth functions look like this. So what we want to do is we want to evaluate M at 4. So what's the small animal population 4 years after these birds decline? So let's put, what we're going to do is put open parentheses everywhere where we see an X or a T in this case. We'll get 400 times 1.4 and then our variable, open parentheses. And now let's put in our 4. So we'll get M of 4 is equal to 400 times 1.4 raised to the 4. Now you need a calculator to do this. And on our calculator, we're going to type in 400 times 1.4 raised to the 4. And when I did this, I'm getting 1536.64. But let's round it up. I mean, it's the number of mammals, so it can't be a fraction. So let's just round this up. How about we say 1537? So 4 years after these birds decline, there's going to be about 1,537 small mammals on this property. Now, our last problem is going to deal with the value of a certain piece of office equipment. It says that the value depends on time, like this, 43.3, 0.6 to the t. Now look at our base here. The base is between 0 and 1, so what we're going to have here is a decay function. Decay functions look like this. Now, a decay function seems reasonable because if you buy a piece of machinery, over time it decays in value. So let's just see how much. What do you think the value of this machine is when it was first purchased? That is when t equals 0. All right, when t equals 0, what we're going to get here is v of 0 equals 43.3 times 0.6 to the 0, but 0.6 to the 0 is a 1, so we'll get 43.3 times 1, which is 43.3. So at purchase, when this machine was purchased, t equals 0, right, no time has gone by, the value of the machine was $43.30. So we bought the machine for $33.30, and what we want to know now is, in this particular problem, what's the value after 4 years? So what we're looking for is this. We want to find the value of this machine in 4 years. So we'll go back to our function, and everywhere we see a t, we're going to write an open parentheses. So we will have v of something equals 43.3 times 0.6 to the something. And our something turns out to be 4. So v of 4 equals 43.3 times 0.6 to the 4. And on my calculator, I'm going to input pretty much what I see. I'm going to input 43.3 times 0.6 raised to the 4. And this is going to give me, let's do it right over here, v of 4 is equal to, I got 5.61168, but it's money, so we're going to round off maybe to 2 decimal places, maybe just right here. So we're going to say that after 4 years, the value of this machine is down to $5.61.